Hello. Okay.
So,
For
sir,
that,
yes, yes, yes.
so we can start now.
Okay, just a moment.
Can we start?
Yes, sir, yes, sir.
Okay. Okay. Uh, Good afternoon to all, and especially our honorable speaker, Madam Miki, Madam Professor Dr. Miki Hasegawa, Madam is present with us, and all the participants. I am welcome you all. It is my immense pleasure to welcome you all to the final day of the AICT sponsors 6-day online AICT Teaching and Learning Faculty Development Program on advances in material science for sustainable development and industrial application, organized by Department of Basic Science and Humanities, Dr. Sudhir Chandra Sur, Institute of Technology and Sports Complex, Kolkata. Over the last 5 days and still today, have lots of eminent speakers and lots of interesting participants through their discussion and the thought-provoking discussions, lectures, and interaction. We learn lots of information, lots of things, and share the knowledge and so on. I would like to I would like to once again invite all the participants and especially Professor Miki Madam. Uh, in this session, we have in this day we have three sessions: session 11, session 12, session 13, where Professor Miki Hasegawa Madam will deliver a lecture the first session. Then session 12 will delivered by Mr. Prashant Devnath, and session 13 will delivered by Professor Dr. Nitin Chattopadhyay, and thereafter we have the online test and feedback and last valedictory session. So this is the roadmap for today's session. So let's start. And now I request Dr. Dipankar Das, the HOD, Department of Basic Science and Humanities. So I request Sir to formally introduce Madam to our all the participants.
Okay, good afternoon, respected Professor Miki Hasegawa and all the dignitaries present on digital platform. So now I'm going to read a short biodata of Professor Miki Hasegawa. Okay. So am I audible?
Yeah.
Okay. So
Thank you.
Professor Dr. Miki Hasegawa, born in Tokyo in 1970, is a renowned scientist in the field of coordination chemistry and photonic materials. She has built an illustrious career through her contributions to academic research, education, and international collaboration. Dr. Hasegawa's passion for science is complemented by her diverse interests, including collecting periodic tables, tea ceremonies, and Japanese flower arrangements in the Ohara style. Dr. Hasegawa completed her undergraduate and graduate studies at Aoyama Gakuin University, earning her Doctor of Science degree in 1998 under the mentorship of Professor Toshihiko Hoshi. She began her academic career at Aoyama Gakuin University serving as a research professor in 1998 to 2002 and associate professor from 2002 to 2010, and currently as a full professor since 2011. Her dedications to advancing chemical science has led to her hold visiting positions at prestigious institutions including the Technical University of Vienna and University of Tokyo. She has also collaborated extensively with the Institute for Molecular Science, further broadening her academic and research horizons. Dr. Hasegawa's research focuses on the electronic and photophysical properties of coordination compounds, rare earth elements, and photonic materials. Her work has earned her numerous accolades, including the Japan Rare Earth Society's Encouragement Award, ADC Award in 2011, and inaugural Spring 8 Exploratory Research Award in 2009. As a highly sought after speaker, Dr. Hasegawa has delivered invited lectures at international conferences across the globe, including in the United States, China, Thailand, and Europe. She has also been actively involved in organizing international symposia, fostering global collaborations in the chemical sciences. Beyond research, Dr. Hasegawa is passionate about inspiring future generation of scientists. She has conducted public lectures, workshops, and outreach programs engaging with students from junior high school to graduate levels. She has also contributed to gender equality initiatives, serving as a mentor and role model for aspiring female scientists. Dr. Hasegawa's contributions to science extend to her numerous publications in high-impact journals. Her studies on lanthanide complex, photoluminescence in rare earth compounds, and innovative materials for energy system have significantly advanced understanding in her field. In addition to her professional achievements, Dr. Hasegawa is a dedicated educator, regularly teaching courses and delivering special lectures at institutions such as Kyoto University and Okonomizu University. Her multifaceted career exemplifies a commitment to scientific discovery, education, and international cooperation. Dr. Hasegawa continues to inspire the scientific community with her innovative research and unwavering dedications to mentoring the next generation of chemists. So this is the short biodata of Professor Miki Hasegawa. So now I would like to request Professor Professor Miki Hasegawa, please continue your sessions. So over the Professor Miki Hasegawa, so you can start your session.
Thank you very much, Mr. Chairman. Professor, thank you very much. It's a really kind introduction for me. So, and also the Professor Das and all of the organizing committee member of such kind of special and distinguished the symposium. So, I'd like to start my talk, and then I hope I can success to share my slide. Okay. Can you see my slide?
Yes, madam. But
And I'd like to. Is it
presentation.
okay? It's a big one. It's not?
It's still working.
Okay. Okay. Just a moment. It's okay? It's okay?
Okay, it is
Mm.
uploading. Okay.
I hope it works.
Uh,
Mm,
yes, madam. But
it's not
uh,
enough
yeah,
size.
yeah, it is visible, but
I know. This is much better, I think.
yeah, yeah.
Okay, good. Okay, maybe I will try. Okay. It's okay for you? Can you see it? My slide.
Yeah, yeah, yes,
Bigger one?
yeah. Okay, ma'am.
Okay. Okay. Nice to meet you, everyone. And then, so thank you very much to join here. So I appreciate very much to talk our recent topic at your very special conference. So I hope my slide is open for you. So the last time I couldn't share correctly. So now I show the cover page of my talk, Helical Molecular Structures as a Key Molecular Design for the Photoluminescence of Layers Complexes. So Professor does, is it possible to see it?
You are, ma'am, changing the slide?
This is, I shared the slide.
Yeah, it is visible. Now
Okay,
you
good.
see the slide?
The
Can you
second
change?
slide. Can you see it?
This is only first slide.
So this is only first slide. So,
Well,
okay.
a little bit of visibility is required more.
Okay.
Ma'am, it is possible to make a presentation mode?
Okay. Just a moment. Can you see it? Is it okay?
Okay, okay.
This is much better, I think.
Better, yeah.
Okay,
Can you,
sorry.
ma'am, change one to slide so that we can assure that, okay, slides
Yeah.
are changing?
Hmm.
Yeah, yeah, it's
Okay,
fine.
okay. No, it's okay. Okay, thank you very much. I appreciate it very much. So this picture is our campus. It's in Kanagawa Prefecture, neighbor from the Tokyo Metropolitan, only 50 kilometers by train. And then, so if you have a time to visit to Tokyo, so please call me. And then, so I will show our institute here. So our institute is belong to the Christian spirit. So now we have the chapel in the campus too, and also the very beautiful stained glasses too. So here is the seaside from our campus. So it takes 20 kilometers. You see there's some ships to see there's some skyscrapers with the ocean, So this is my group. So, and then, so recently I have a good chance to connect to the Indian professors, especially Professor Shinha could visit us with Professor Otsuki, the Nihon University in Japan. Also, we hold a special symposium with him and also Professor Ismail from Spain. So now you see the Professor Shinha was so kind and very educative for or even for our students. So Japanese student is so shy, and then so we have to be more open to contact each other. And additionally, so this is very hot news because recently we had a new colleague from India. So Dr. Nikita, she will be a group member of my research group as an assistant professor. So now so we have a good atmosphere for Indian researchers because she will be here with us to investigate the ransomite luminescence. So at first, I'd like to introduce briefly our research interested. The the important keyword is only two: rare earth elements and linearly polarized luminescence. Now, why we use rare earth elements? So element is not element in this case. So I mean, we'd like to make the new concept as a molecule, including the rare earth ions, So if we treat the luminescence of rare earths, we have to consider the four keywords. So rare the energy transfer, photoantenna effect, and FF transitions. So additionally, we'd like to consider the transition dipole moment if you derive the linearly polarized luminescences. So, excuse me, just Japanese, but you can understand. So, what is the rare earths? So, rare earths is very useful for the efficient driving. So, efficient to make the good and then so flexible the metal parts, and also we can use for the strong magnet. And also, we can see there's some kind of the sensor even for our life, Also, it's not that the act as a good catalyst for the organic synthesis for the medical procedure, so on, So that is one of the example. The luminescence color change by using the europium and the terbium. Europium and the terbium luminesces in red and green respectively. But after the mixing of these complexes, you can see the yellow emission. That color comes from both luminescence of red and green. So not yellow luminescence, but we recognize yellow. That is very important point. And then, so this phenomena is also used for the security ink to keep our economy. And then this is our investigation map. So this direction, we see the application. And this direction, we see the fundamental science or so on. So this direction, we see the category of the materials, organic compounds and inorganic compounds. So between them, among them, we see the coordination chemistry. We can combine each other organic and inorganic chemistry. So additionally, so we treat some of the commercial available, for instance, the cosmetics and also some space engineering. So in this talk, I will introduce briefly about the quantification of the taste, It's kind of the artificial tongue, our tongue, Also, from the viewpoint of fundamentals, so we have three or four categorized theme. So one is a molecular film, and one is an interfacial complexization between the substrate and the organic or the inorganic materials. And also, mainly, I will talk about the discovery of the conceptual unit as a rare earth elements. That is the main talk of this talk. So our team was established in 2002, mostly 22 or 23 years old. And then, so the continuously we focus on the molecular chemistry. So most important keywords is our interesting for 0 to 1, from 0 to 1. That is very important to make the new concept. So that is the category of the function of a series of ransomware. So for instance, so the function means the some good or the efficient the usage for our life. For instance, catalysts, conductors, magnets, and light emitters. So in the case of the samarium SM, it has a three main function: magnetism, conductivity, and luminescence in pink color. However, so it comes from the same reason of the inner transition metal electronic configuration, And then so the function comes from the distribution of the elements, and then so your 4f orbitals placed in the inner core of the metals, So the outer sphere has s orbitals. It's very interesting. And then so the 4f electron is a key to design such kind of the functions. However, nobody succeeded to obtain the luminescent magnet. That is the key point to read the new science also. So by using this electronic configuration, so we can see the unusual the molecular structure by using the rare earths, for instance, caged types and helicate and helical. So in that case, so you see the triple strand structure. So by the one lanthanoid and two chromic ion, And then so it also has unusual luminescence as an upconversion system. So, and then this helical molecule, by using the hexapyridine ligand, and then makes a helical structure as a mononuclear compound, So by the viewpoint, from the viewpoint of the synthesis of the molecular luminescent molecules, so we have to consider the principle, and also evaluation is very important. So it is this is some of the key word to consider the molecular design for the luminescent material, and this is energy conversion from UV to Vs or the vice versa, and for the excitation of the organic ligand to accelerate the intermolecular energy transfer from the ligand to the center metal. And third one is energy relaxation by thermally or the luminescent, So that both are very important to consider the luminescent efficiencies. And the last one is the light emitting of the lanthanoid themselves. So additionally, we have to consider this one, excuse me. So I have to change the color. So this molecular, this is a more intramolecular energy transfer. That is most important to design the emissive, high emissive lanthanoid complexes. So that is one of the cartoon to understand and to design the emissive lanthanoid complexes. So as I told you, about the luminescent mechanism, it comes from the energy transfer from the light irradiation, the UV irradiation excited at the higher excited state of the organic ligand, and then after the energy transfer to the F elements, we could obtain the FF luminescence. At that time, we have to consider the superimposition between the emission of the pyraclic system and then the absorption of the F elements, and then it occurs the efficient energy transfer. So this is a split F band F levels. So we called the decay diagram. It was published in 1936, and then the band position is mostly same. It's very stable. That's why europium luminescence always in red and terbium luminescence always green from this principle. So the question of today, I will talk about the recent topic. What do we need to design the highly luminescent and stable lanthanoid complexes? So now we have to think the conceptual rare earth element. So by using the molecular chemistry. So we see there's some 3 keywords to design such kind of rare earth elements. The first one is the structure and luminescent stabilities, even in solution. And then the solubility should be kept even in solution. And then finally, flexible modification is also available by using the organic synthesis. So this is our answer, one of our answer. So we'd like to make the helical structures, that is very important to keep the stability and solubility for the new materials. This case, so you see the mononuclear and then tunable means the organic synthesis is a powerful method to understand to keep the next design. And the third one is a helical structure. So it keeps the polarity and makes solubility. And then so the this part, you see the chelate rings 1, 2, 3, 4, 5. So it has 5 chelate rings. So it means the chelate effect will available, and then stability is so high even in the solution. And finally, so europium is trivalent, and then 2 nitrate minus minus, and then ligand is a neutral. So finally, this molecule is ionic molecules. That is also the very good keyword to expand the order to apply for the next material. So this is the exact molecular structure. So this is the chelate rings, 5 chelate rings. And then so this is a polarity, not marked growth cycle. That is very important to keep the solubility. So now we published some of them by using these molecules. This molecule is a mother molecules. We can tune by organic synthesis to the reduced one. So and then so it is applicable for gas sensing, and also we can expand the pyracline system, and then we can tune the energy levels to give us some different layer acids. So from bipyridine to the phenanthol line, that is also very important. And also after the changing of this part, the ethylene diamine, so we can induce the linear circularly polarized luminescence. So by using the chiral species here. And also we can tune the helicity, And then finally, after the reduction of the atomizing group, so we can tune the many kind of the derivatives here. So this is amphiphilicity, and also this is the highly water solubility keeps the molecular structure too. So furthermore, so after the changing of the anions nitrate change to the carbon the BDC by carboxylic benzene, and then so we can make the chain complexization and also the oligomeric brush on the substrate. So this is a kind of the cartoon to make the sense about the number of chelate rings to keep the molecular stability, and also this direction shows the transition energy and energy donor levels of the ligand and energy and the acceptor of the lanthanide, So in the case of the europium, so tapyridine or the bipyridine will act as a good energy donor to induce the very efficient energy transfer, And then finally, we got the very high and strong color luminescence from europium or so on. So this is also the single crystal X analysis results of the europium complex. So it takes the helical, and then edged pyridine interact each other with a very short distance, between the ternary pyridine moieties. And then so after the measurement of the synchrotron XRPD, so we can make the electrostatic potential from the experimentals. And then so this was observed under the dark. This was under the UV light, So the result completely differ from each other. So, and this, for instance, this one, blue color, changes to the pink. So do you remember the tapyridine will act as a good donor system to keep the efficient energy transfer, induces the strong luminescence of lanthanide. And then so it looks the tapyridine more than pyridine in this case at the high at the excited state. That's why we could obtain the very bright luminescence even in a europium or so. So that is the result of the observed luminescence of europium and terbium. So in these cases, so europium has a very high luminescence even in acetonitrile over 12%. And at the room temperature, the solid state complex keeps the very high luminescent over 50%. And then so europium complex has no temperature dependencies. However, in the case of terbium, so the luminescence is very weak. Luminescence intensity is very weak, and also it demonstrated the temperature dependencies, strong temperature dependencies. So at the room temperature and the low temperature, the quantum yield is drastically different, different each other. So it comes from the principle. It means so this is a ligand after the excitation by UV light. So the triplet state will act as energy donor. But in the case of the terbium as the energy acceptor level, so it's very consistent to keep the energy levels, and then at the room temperature, so backward energy transfer is available, and then so finally we couldn't obtain the very bright luminescence from the terbium, but the europium has a luminescence strongly more than the terbium case. And additionally, at the low temperature around the liquid nitrogen, so the backward energy transfer interpret, the forward energy transfer is available more than the backward. And then finally, so the quantum yield is mostly 100%. So we checked the centimeter dependencies. So if we change the centimeters from this one to other one, so we could see the uniform from the viewpoint of the X-ray structural analysis. And then so for instance, the interatomic distance between the centimeter to the combining atoms, in this case nitrogen or the oxygen, so it aligned to the along to the latent contraction. This is the interatomic distances, or this is the ionic radii. So it means it's a very unusual cases. So it can keep the uniform if we change the centimeter. So as a centimeter, so these molecules. So if you use the europium, we can see the very bright luminescence color in red. And then after the solubility, after to make the solution of the europium into the ionic liquid, it's also very useful because so the luminescence can keep very bright luminescence even at 100%. 100 degree. And then so we checked the energy transfer efficiency by the changing the molecular ratio, molar ratio of the ionic liquid and acetonitrile. It means the viscosity changes by using the different amount of the ionic liquid. We can check the energy transfer efficiency by the luminescence lifetime and so on. And then so we can say the high sensitivity on the viscosity were found in these cases. And then so we checked the molecular structure changes by using a TDDFT calculation calculated by Professor Hatanaka, Keio University. And then so she found the new insight, because during the energy relaxation from the excited singlet state, so we see this the inter-system crossing to be a excited triplet state. So this level makes a different molecular shape. The yellow one. So yellow one is different from the other cases. Red, green, and blue. Blue is the ground state, So this is a triplet state. This is the emissive state of the terbium, and then europium, excuse me. And then so finally, so this viscosity will prevent such kinds of molecular shape change. So due to the high viscosity, and it's very difficult to move during the energy relaxation. So by using this system, we try to change the ionic oxidation state. So the europium makes red luminescence if it has a trivalent state. But after the reduction of the europium, so we will see the blue color emission. So we use such kind of the electric cell, and then adapt the current, current. You see, the red color becomes weak, and then so recovers. And then we check the CV and then the luminescence intensity change of the europium 3+, in this case, this one, So it means, so the europium 3+ can change this oxidation state from 3+ to 2+, and then so it's reversible. It means the molecular shape is very stable even in ionic liquid. And then it's very useful to make the next emissive material by using the europium 2+. This is. So now we change this part, azometine group, to the CN single bond. So this is the azometine group molecules. And then so if we reduce this site from double bond to the single bond, so the energy excited state becomes higher than the mother complex. And then finally, we could obtain the very bright luminescence from terbium even at the room temperature and the solution. And then additionally, we can change this part to the other, this one, and also this one, or this one. So I will introduce briefly if we added some stearic acid. So this makes some molecular shape change. Excuse me. So and then so this part act as also the a kind of the core for the molecules. And then so the molecular the quantum yield of the luminescence of terbium is much higher than the mother complex, So the 55% in chloroform, and then the solid state over the 66%. So even in the terbium. And also, it acts as the hybridized conformation to find the graphene seed. So graphene, the graphene cannot see, and it's invisible for us. But after adding these samples, so the graphene is hydrophobic, and then so we can find the place of the graphene by using these amphiphilic molecules, And then this is also some of the new insight to understand the molecular transformation. So by using the amphiphilic moieties, so we see the 2, 2, 3 complexes. So 2 means the 2 europium centers and 3 ligands, So it's a very complicated. It was unexpected result. And then so after the comparison of the synchrotron XRD and luminescent lifetime, we could assign these components differ from each other from the different structures. So we'd like to move to the water solubility by using this component. So unfortunately, this mother complex is unstable in water. We cannot see the luminescence. It comes from the dissociation because it's unstable in water. And then so we design these molecules to carboxylate after the reduction of the mother complex. We added some 2 carboxylate, and one will act as a water solubility and hydrophilicity, And then so the another one will act as an intramolecular coordination to make such kind of the encapsulation molecules. And water is very important to our life, but sometimes europium luminescence disappear by the quenching effect of waters, water vibration. So makes a resonance so between the luminescent band of europium or so. So And then so this capsulation model is very suitable to keep the luminescence because only one water will attach to the europium, and then so the effect will be less than the normal one, you know. So successfully, we could observe the very bright luminescence even in water by these half capsulation molecules. And then from the Horrocks equation, this is also a very unique equation published by Professor Horrocks. And then so we can estimate the number of coordination water from the lifetimes in D2O and H2O. And then finally, so in the case of the europium, so it can coordinate one water molecules. Similarly, so in the case of the terbium, also one water molecule can contact to terbium. So it is nicely results. And then additionally, we change the pH, so from 2.6 to 9.7. And then so we could see the spectral reversibility from 1.9 to 11.7. That's a very wonderful stabilities. And then so the half capsulation system is very useful for this kind of the material. Furthermore, we check the toxicity of these molecules by using the zebra fishes. So here is the zebra fish eggs, you know. After adding our samples, the one day later, so we see the baby fishes here. So it means the toxicity is negligibly low. So maybe we will apply for the gadolinium because gadolinium is a useful agent for the MRI for our life, for our sensing, you know. So finally, we could summarize some of them in this paper since 2014 to recently. So this is another possibility. It can be applied for the theoretical method. So the landmine is very difficult to estimate the molecular structure and then molecular packings. As I told you, the outer sphere is s orbital, so it's spherical, and we cannot estimate or we cannot simulate the molecular shape more than the D block materials. But in this case, as I told you, it's uniform, and then we could make the new parameters for a series of lanthanide by using these experimental results. And then Dr. Nakayama, he belonged to the company Conflex. He uses these parameters with our groups, and then so we succeeded to calculate the estimated molecules and the molecular packings. So the yellow one and the green one calculated and then observed results respectively. And then you see the molecular shape is completely or mostly similar. So by using the calculation with our parameters. So that means, so it's very, very useful molecular system to estimate to estimate and to determine the new parameters for lanthanide. So it was awarded from Japan, Chemical Society of Japan. So the last part, so I will talk about the complexization of this complex as a rare earth element, because as I told you, so the nitrate can replace to the benzene decarboxylate or so on, and then it makes chain complexes, and then so we can change the color of luminescence by using the different ratio of the europium and the terbium complexes. And then the second part, so we can make immobilize the system by using these chain complexes onto the quartz substrate. And then so we can apply for the nano particles or the microbeads. So the first one, so we can try. We tried to make the immobilize the system by these molecular chains. So, and then, so this one, we evaluated the structures. So by using the XPS. So for instance, this is the first generation. So you see the two band of N1S XPS. It comes from the ligand here. And then the violet one comes from this one, nitrate. And then after change this nitrate to the BDC, benzene decarboxylate, so we cannot see this side here, this one. And then the next step, next generation, we also see the next nitrate here. Excuse me. So it means, so this molecule can make a step-by-step, the layer by layer deposition onto the substrate. However, so we cannot see the XRPD patterns, only the halo pattern here. Why? And we wondered, so this molecule cannot make this kind of the straight chains. This is the powder patterns of these powders, but this is completely different each other. So, and then we have to check this molecular chain bending, outer sphere for outer side to the inner side. And then, so we checked the luminescence and the luminescence lifetimes and the luminescence quantum yield. So first generation is this one, the quantum yield. And the second and the third generation after the deposition, so we can change the strength quantum yield. And then, so moreover, so the luminescence quantum yield decreases. It means, and then so stable. So it means maybe the structure will be this one. So the chain will make the aggregation, not makes a flower, not flower structure. So, and then so we also checked the polarized absorption spectra of these molecules. And then so it is very useful by using the ATAL method. So it's a new method by using the evanescent wave on the substrate, And then we can estimate the tilt angle of molecules, and then it was about the 70 or the 60 degrees. So finally, we estimate the molecules makes a disaggregation from the viewpoint of the ATL polarized absorption and the luminescence lifetime and the luminescence quantum yield. So if we change the substrate from the plate to the microbeads, so microbeads makes the straight chain growing, we expected. And then finally we succeeded such kind of the molecular shapes and the molecular systems. For instance, this one, the red color luminescence of this one, so or the chain structures molecules luminescent under the UV light, and then so these silicon microbeads include the ferrite Fe2O3. So the microbeads attached to the magnet site, So you see the first one is the dispersion, but after reach the magnet, so the transparency is higher than the first one. So this is terbium 2. You see the dispersion under the UV light luminescence by terbium green light, and then after reach the magnet, so the transparency of the solution dispersion is much higher than the initial state. Okay, so that is also good. So the last part, so I will introduce unusual luminescent. So especially the linearly polarized luminescence we call LPL by using the amphiphilic molecular system of europium or terbium. As you may know, the circularly polarized luminescence we call the CPL is a very useful recently. So and then so there are many literatures or reported. And then so this case, so we can categorize the discrete system and then so the interaction or the aggregation induced CPL. So discrete system was published by Professor Kaizaki. They succeeded to obtain the 1.38 the polarized the luminescence dissymmetry factor, so the G lumi value, and also this one, the Professor Kawai, also they succeeded to obtain the very beautiful luminescent CPL materials as a discrete system. And then so recently, so the Professor Hasegawa, another Hasegawa, succeeded to get this kind of the chain complexes. So it's a kind of the polymer system, metal polymer coordination polymers. And then so the just last year, so I didn't replace yet, but the last year they succeeded the highest value 1.53. So this is aggregation system by Professor Yuasa 1.45. That was the highest one, but recently 1.53. So it was published in Angevante. So and then so it means it has some molecular trick using the chirality, But in this case, in the case of the linearly polarized luminescence system, LPL has no principle. So we have to consider the transition dipole moment, TDM, So in the case of the crystal, so mostly the dipole moment canceled out each other in the crystal and in the solution. So the direction of the TDM is randomly exist, And then finally, we focus on the Langmuir-Brodet films, LB films, and then we can see the quite stable structure and then makes the alignment of the TDM. And we succeed to get the LPL active films by using this method. It was summarized in recent our review. So this is one of them. So this is collaborated with Professor Yamanaka. And then so they succeeded to make this, to synthesize these molecules we designed together. And then we observed the linearly polarized luminescence. This is the angle of polarizer. And then so we see this intensity, this band intensity changes by using the different polarizing angle of the polarizers here. So it is the LPL active films by using this method. And then so this motivation is very important. So because amphibolic system keeps their own electric structure, so not canceled out the TDM. So it prevent by the alkyl group. So also we checked some of the examples. For instance, this was published mostly 20 years ago. So they succeed to get this kind of the European complexes, but no discussion about the LPL. And then the Professor Alan Higer, so they also succeeded to observe the linearly polarized luminescence by using the stretched polymer films. In this case, they use the polyethylene group, including this European complex. And then so they observed this one. And then also our group also uses the polyvinyl alcohol. And then so in this case, we contain the phenol line as the photo antenna molecules. And then after the stretching of this polymers, so we adapt some of the europium nitrate or the terbium nitrate is the spin coating method. And then finally, we could obtain the linearly polarized luminescence. And now, so we checked the other cases. This case, so Professor Kitchen and Peacock, they succeed to obtain the CPL LB film of europium. But even now, so we couldn't have some kind of the result of the LPL not enough to discuss. And then so we'd like to change or control the linearly polarized luminescence by using the organic compound change. So we published, published in the Pure and Applied Chemistry 2 years ago with Professor Yamanaka. So firstly, we observed the linearly polarized luminescence in 2019, as I told you already. But in this case, so the luminescence quantum yield is less than the solution system. So in solution, this molecular compound, the European compound, has over 30% luminescence quantum yield. What is the less? We'd like to realize the efficient energy transfer and the energy and then so the efficient strong luminescence of europium. So we changed the some medium contained with this photo antenna, amphiphilic photo antenna. So with aceleric acid, this is the first one. The quantum yield was 5.8. It's enough, but not enough. So and then we changed the MPBA as a medium for this compound because the strategy is very unique and very easy. So stearic acid has no aromatic pair, but in this case, naphthalene. So naphthalene makes a pi interaction even in the film system. And then so MPBA has a methyl group, and then it will prevent the pi interaction between these molecules in the film. And successfully, we could obtain the high polarized, linearly polarized effect, and also the high energy, high luminescent quantum yield. So this is a medium change. So additionally, we changed the TDM, the direction of TDM. So it means the initial compound has the long alkyl chain here, and this is the coordination site to europium here, and then we change the place of these the substitute, here. So it's a change the direction of TDM. So what happened? Change we checked the pi isotherms, so this direction is the area for our molecules, and this is the surface pressure, and then so we can see the sum of the area, molecular area for for one molecules, averagely. And then so we check the synchrotron XRPD. So this is not powder, but we can observe that we change the machine with some new attachment we developed with some researchers, Professor Kimura and Professor Takada. They are very good research collaborate researchers. Excuse me. And then so finally we could estimate this interlayer distances from here. And then this is a relaxation process of these materials. And then so finally we could obtain the very high luminescent quantum yield of europium. So now we'd like to observe the LPL again. So by using the different direction of TDM. So these 6 substituted naphthalene moieties, we check the LPL under the different pressures. But the quantum yield, luminescence quantum yield is not so high, so more than the previous one. So finally, we can compare with the first one with this one. So this is the highest ability as a linearly polarized luminescent material. So additionally, we tried to make the artificial tongue with a researcher from electric engineering, and then so by using the same system, this is a result of the taste sensor. So with Professor Yuki Hasegawa, and then so we use this LB films as the sensor to the the sake, the alcohol. So in Japan, there is a many brewery of sake, and then so it's a different taste each other. But the quantitative discussion is difficult for the tasting, So you like or not, or it's stable taste or not. It's very important and the different viewpoints. So in our case, we have to make the quantitative sensor for our taste. At first, the solution is very useful for the experimenters. Then finally, we could find the accessibility and the potential differences is much higher than the normal stearic acid LB films. So that europium or terbium, if we use the lanthanoid, the sensing ability is the 3 times higher than the organic compounds only. So finally, I'd like to summarize about my topic. So hexadentate pyridine derivatives are very useful for the lanthanoid complexes for the various emission enhancement resulting. And then molecular shape and then the surfactant system is also very unique to induce the linearly polarized luminescence. So 2 months ago, just we published this book with Professor Jean-Claude Bunzli and Susan Carter. They are very good editors, so they provided good suggestion to summarize these topics. And then you can see more detail in this book if you have interest. So finally, I'd like to thank to my colleague, especially Dr. Hitomi Omagari. Now she moved to another national institute in Japan, and then Professor Kawaguchi. He is a very good researcher at Spring 8, and then Dr. Nakayama is a good collaborator for research, even in the calculations and then theoretical chemistry in complex. And also I thank to the financial support from the government and some project and then some agencies. And then finally, thank you very much for your kind attention. Thank you very much.
Yeah, thank you. Thank you so much, madam, for this wonderful, wonderful lecture you
Thank
share
you
with
very
us
much.
and enlighten us. And I think all the participants also gain lots of knowledge and lots of information from this presentation. Now this platform is open, so any participant or any faculty members have any query, they can ask to madam
Thank you very
or any
much.
kind of.
Appreciate. Thank you very much.
I want to have one question to Professor Hasegawa. Can I?
Yeah, sure, madam.
So, Professor Hasegawa, this is Somu Mukherjee from Metallurgical Engineering, Kazi Nazrul University, India. Actually, I'm actually materials background, engineering background. I just want to know from you, madam. You are talking about LPL concept, that is linearly polarized luminescence. So,
Yes.
is it applicable? The concept is also possible in case of a glassy based system, or even in extended to composite. Will it be possible in those cases, or is it only restricted to this type of chemistry things?
Thank you very much, Professor. That is a very good point. And then, so it's very difficult question. So at the moment, we succeeded to obtain the LPL in the molecular system, and then the size is very small, only 1 by 1 centimeters. So I hope, and we hope, to apply for the commercial available, but the molecular system is very sensitive, as you know. And then, so the student makes the training to get the same quality films. At the moment, there are 2 options. So for the application, so the one is automation is very important to use the mechanic. And also the second one is stability of the molecules. So, and then, but if we apply for the informative transformation system, for instance, the optical fiber or so on, so the one fiber can transport the 2 or 3 different information by using the different angle polarized system by using the LPL. I hope, but we don't know yet. Thank you.
Okay, madam. Okay. Actually, I was wondering because so many ceramic materials are also good luminescent.
Yeah.
Actually, we generally tendency to only observe the luminescence behavior and don't go to the details actually. So that's
Yeah.
why I think maybe that's why I have asked this question, madam.
Okay. That's
It
good idea.
is actually a new concept actually for me actually.
Thank you very much. So actually, there are not so many information about the LPL of lanthanide complexes. That
And
is quite
another thing I want to know from you, madam, just for my knowledge enhancement,
yes, please.
is it strictly restricted only to crystalline structure, or is it also applicable for amorphous system?
Oh,
This
yeah. Okay.
LPL, will it be applicable for amorphous system?
Yeah, thank you very much. So, in the case of the amorphous system is also very important as the sensing. So, on the immobilized material, So, that is very good point of view. And then, so we didn't have no idea how to read and then how to make it. But the amorphous is also difficult to make the isostructures or so on. But it's a good idea. I had no idea at that moment. Thank you very much. Good.
Okay, madam. Thank you. Thank you for
Thank
the
you.
enlightenment. Thank you, madam.
Thank you very much. Very helpful.
Is any question from other participants or other faculty members? Saurabh Bhattacharya. Okay. Is any response from other faculty?
There are many participants.
Yeah,
I
yeah,
appreciate very
yeah.
much. So I'm very happy. And the many comments. Thank you very much. I also learned many things.
Yeah.
Thank you very
I,
much.
last I checked that in check box somebody is write their question. Uh, if any right. Okay. So,
Good system.
okay, madam. Yeah.
Yes.
And there is you mentioned that one thing that the if there is anybody wants to collaborate with you, then what are the possibilities and
Yeah.
how they can be?
Of course. So if you have any luminescent material, so please let me know. So and also if you have a chance to visit to Japan, so welcome your coming. So please contact me. So
Yeah. I think
anytime.
many of faculties,
Seriously, madam,
students,
I am very
PhD or
much
postdoc.
interested, madam. So actually,
Okay, good.
actually,
So,
I work in different electronic materials, and some of the materials are good luminescent, but I have no
oh,
in-depth knowledge regarding that part, and
really?
it will be really helpful and also would be very much what
Yeah.
I should say.
Okay, very much.
I,
Actually, the instrument to observe the linearly polarized luminescence is not commercially available. I changed with the company, and then that is only one in the world, I think. So if you have interesting, to observe some luminescent material, so our instruments are always good state, so you can use it. So Professor Soma, Somia, is it
yeah,
okay?
yeah,
So yeah.
yeah.
So you can contact me. So anyone can contact me. So it's very easy. It's
Thank
easy.
you, madam. Thank you, madam,
Yeah,
for
of
your
course. So
guidance.
maybe you know my email address from
Ah,
some
we'll
places.
share it with yeah.
Yeah. You can share that. Thank you very much. So I will.
Uh,
I will send my email address to all, so you can
Yeah,
contact
yeah,
me.
okay.
That is very
Okay.
easy.
Yeah, easy.
Yeah.
Yeah.
Mm.
That is very kind of you, sir, ma'am.
Thank you very much.
Anybody has any query? Okay.
Okay.
Okay. Uh, so just a few minutes more, because from one token of appreciation from our side, we will share. This is a digital platform, so we will share it by digitally. One.
Okay, good.
স্যার ফোন করছে কেন স্যার কি হলো
Thank you very much.
Dr. Dipankar sir, are you online?
Yes, sir. Yes, sir. Yes.
Yeah. Okay.
Okay. So thank you, madam, for your
Thank you.
beautiful lecture, and we have learned a lot of things. So, and future we also again arrange this type of program, conference and FDP, so that we get another chance to listen beautiful lectures.
Thank
So
you very
now,
much.
as the program has been conducted through online mode, so we have a digital memento. We have a digital memento, and from Dr. Sudhir Chandra Sood Institute of Technology and Sports Complex, JS Group. So I would like to request Dr. Biswajit Das to share digital memento to Professor Miki Hasegawa as a small token of appreciation from our college end. So I request, madam, please accept this digital memento from us.
Thank you very much.
Welcome, ma'am.
Is it visible?
No, it is not visible. Not visible.
Oh, beautiful. Ah, Rishi. I'm very happy.
Thank you, madam.
Thank you very much. Could you send it through the email
Yeah.
too?
Yes,
Yeah, I
yes.
appreciate very much. Yay!
Thank
Yeah, thank you very much. It's
So
beautiful.
I would request all the participants, please switch on your video so that we can capture the photo and we man
Group
and
photograph. Yeah.
group photo. So switch on the video, and I request. Okay.
Thank you.
So my video is not open. Okay. So, request all the participants, please switch on your video. Dr. Biswajit Das, please sir, switch on your video.
Yeah, I'm already.
হলুদ দিবেন তারপরে সবুজ দেখতে হবে
Sir, your video is not coming.
Okay.
And you take a screenshot, sir, please. You take a screenshot.
Yeah. Just a moment.
Okay. So thank you all
Yeah.
for your kind support. So now you can switch off your video. Okay. So thank you, madam.
Thank you
Okay.
very much.
Good afternoon.
Thank you very much. Have a nice day.
We'll see
Yeah,
you
thank
soon.
you very much. Nice to meet you again. Thank you.
So what to Dr. Biswajit Das, please go ahead.
In our next session is session 12, where Mr. Prashant Devnath will deliver a lecture on biodiesel plant in India. He is a Chief Operational Officer and CEO, co-founder of Millennium Technology Private Limited. So because this session has been ended little early, as per our schedule, the session 12 will start at 3:30. So now, during this time, we can share uh, or we can discuss something. I'm asking that
Sir,
to join. Yeah.
sir, please, I should stop the recording. Then we can give some instruction. Okay.
Okay.
Shall I? Okay.